This is Daniel Coosbury, and in this lecture we're finishing up our talk of statistics with measures of dispersion. So the last lecture we looked at measures of center, and I like to think of it kind of based on that histogram we drew originally. Was measures of center kind of told you where the center of the data was, and it might be this high middle part or wherever this bell is the highest. The measure of dispersion is a way of kind of talking about how spread out the data is. For example, you can look at kind of how far away these bars are from this high middle part, or imagine another histogram that looks more like this, where the middle is very high and it's not actually spread out very much. So we could say this one's more dispersed and this one's less dispersed. Another word for dispersion is spread. This one's more spread out, this one's less spread out. And so these are kind of the two big things that we're interested in when talking about a data set, is what's the middle of it, what's the center, and then how dispersed is it, or what's the spread of it. So center and spread are kind of a way of summarizing 12.2 and 12.3. So we're going to look at two measures of dispersion in this section. The first one's sort of simple. It's called the range, and you might have seen this definition before. It's the highest data value minus the lowest data value, and it describes just kind of how far apart the two extreme values are, and that's the measure of dispersion. So it's a really simple thing to do. Look at a data set. So here's a small data set. The range is going to be the highest value minus the lowest value, which is going to be 11 minus 2, or 9. So you can say that this whole data set contains a range of any numbers between, or any 9 numbers, so to speak. It doesn't contain all 9 of them, but it's 9 numbers wide. Goes from 2 to 11. That's the range. It's a little simplistic, and it's used for a few things, but it's not the best measure of center. Measure of dispersion. The best measure of dispersion is what we're going to spend most of this section talking about. It's the standard deviation. And let me just kind of throw a formula at you and then kind of tell you how we're going to find it. So we're going to represent the standard deviation by a little s, and the formula kind of looks like this. It's a little scary. Sorry. So S is going to be the sum of a data point minus the mean squared. Then you add them all up, sum it, and then you divide by n minus 1, and all this stuff is inside of a square root. So kind of to break this up into this little box, to find the standard deviation, the first thing you want to do is find the mean of the data set. So find this little x bar here. And then you want to find the deviations of each item from the mean. So the data item minus the mean, so that's x minus x bar. You want to find that. Let me write it out here. You want to find x minus x bar. That's not a terribly hard thing to do. You find the mean, we've already done that, and then subtract from each data point the mean. And then once you've done that, you want to square each one of those deviations. So we'll call this a deviation. How far away is this value from the mean, or how far apart they are. Then you want to square those. So you do x minus x bar squared. And then you want to sum all those things. So this is the deviation. You square all the deviations, and then you sum all the deviations. I know this is kind of scary math stuff. You sum all of them, and then you divide the sum by n minus 1. And then you take the square root of all that, and that's this formula up here. So I'm putting this up here for procedure. I know the procedure is not going to make any sense until we see an example. So let's just skip ahead to an example, and you can look back in this video at this little blurb if it's helpful. This is in the textbook too. Okay, so this data set represents the age of the 5 oldest U.S. presidents. I think this is the inauguration age. Yeah, age of inaugurations of the 5 oldest presidents. So it's a data set. It includes 5 numbers. There they are. And we want to find the standard deviation. So we'll go through that process in that yellow box. The first thing we do, this is step 1, is we're going to find the mean, which add all 5 of those numbers up, divide by 5, you get 66. So that's the mean. It's not that exciting, really, but there's the mean. The next thing you do is you find the deviations from the mean. How far away is each value from the mean? Are they like a few units greater than the mean or a few units less. You do that by taking each one of these values, all 5 of these, and subtracting 66 from each one of them. So here's the data values. Here's the data values minus 66. So take the data, subtract 66, and this tells you how far away each one of these values is for the mean. So 69 is 3 units higher than the mean. 68 is 2 units higher than the mean. 65 is 1 unit less than the mean, and so on. It's not super exciting stuff, but that's kind of what these numbers mean and why we're interested in them. We call them deviations. How far away are they from the mean? Okay. Next thing we do is square the deviations. So this is a continuation of that table. There's the data. You subtract them to get the deviations, and then you square the deviations. So 3 squared is 9, 2 squared is 4, negative 1 squared is 1, negative 2 squared is 4, negative 2 squared is 4. So this is the squared part. The reason you square the deviations before you add all of them up is because it's kind of a weird little math thing. If you were to just add up these deviations, sum them all up, kind of like you add up to get the mean, if you just add these things up, you get 0. And it turns out that happens every single time. If you take your data, subtract off the mean, and get the deviations, you add up all the deviations in any data set, you're going to end up getting 0. And so it's not actually a very helpful thing. So what the statisticians figured out is if you square all of them first, you end up with all positive numbers, whereas some of these are negative. If you square all of them first, you end up with all positive numbers, and then you can add them up without getting 0. So that's that actually ends up turning into something useful. If I add all these up, I get 0. I don't know anything about the deviation from the mean because it's 0. But if I square everything, everything becomes positive. I add them all up, I get 22 as my deviation. So I finally have some sort of number that I can use to describe the deviation from the mean. All right, let's finish this formula up. So it said you want to subtract off the mean, square the deviation, and then add them all up. So that's step, let me see if I can kind of name these things. So X bar was step 1, this is step 2, this is step 3, adding them up was step 4. Step 5 is going to be dividing the sum by n minus 1. So dividing the sum, which is 22, by n minus 1, n is 5, minus 1 is 4. So 22 divided by 4 to get that. And then to square root it to get the standard deviation. So you square root that, square root 5.5, and you get 2.35. So it's an awful lot of steps to this. It's incredibly messy to do by hand. Most graphing calculators know how to do this. You can stick your data in and tell it to give you standard deviation. Computers know how to do this, which is really helpful. But if you need to do it by hand, these are the 6 steps you need to do. The first one is find the mean. That's the mean. And find the deviations, square the deviations, add them up, divide by n minus 1, and square root that. That gives you a measure of spread. So the standard deviation itself is kind of a hard number to understand. It's telling you the standard deviation is 2.35. It's a number that describes how spread out the data is. But that number probably doesn't mean anything to you, which is fine, because this is the first look at it. So let's look at an example now of 2 data sets that have the same mean and different standard deviations. Okay. We have samples, 2 samples, sample A and sample B, and I want to find the standard deviations of both. And to do that, I need to find the mean first. So step 1 is find the mean. This is step 1. So there's the mean of each one. They both have mean 20. If you add them all up, divide by 7, add the second data set up, divide by 7, you get 20. That means that on average, both of those samples are the same on average. However, we might find out one of them is more spread out than the other, and this is really where standard deviation comes into play. So now, here's kind of a summary of the first part of the standard deviation. So this is step 2, subtracting off the mean. Step 3 is squaring it. Step 4 is this. So I'm just kind of marking this. This is sample B. Step 4. And so these are the deviations, the squares of them, and the sum. Deviations, squares, and sum. I'll let you kind of, if you want to pause the video and look at some of this, but I just didn't want to spend time doing all this arithmetic for you. It's already done. Okay, step 5, let's do sample A over here. And let's do sample B over here. Step 5 is dividing the sum of the squares of the deviation by n minus 1. So we're going to do 28 divided by n minus 1. N is 7. So 28 divided by 6, and that's going to be some decimal. 28 divided by 6, or 4 point, I'll round it up to 7. How about that? Sample B, going to divide the sum of the squares of the deviations by n minus 1, which is 7 minus 1. 700 minus 6. And this turns out to be 694. Okay, now I'm going to compare these in just a second, but I haven't found the standard deviation yet. So step 6 is to take the square root of that. So S is equal to the square root of 4.7, which is just about 2.16. I'll round it to that. All right, here S is going to be equal to the square root of 694, which is just about 23.34. Okay, I'm done. So what I've done is I found the standard deviation of both of these samples. And here's the samples again. The first sample, they each have a mean of 20. They have the exact same mean, but the first sample has a standard deviation of 2.16, whereas the second one has a standard deviation of 23.34. Remember that standard deviation is a measure of spread or dispersion. That means that the sample B is spread out a whole lot more than sample A. Or sample B has a much higher spread than sample A. All that is to say is if I were to have like a histogram of this data, they would both have means of 20. You know, the highest parts would be like that, but sample A would not be spread out very much, whereas sample B might look more like this. You can see the mean is 20, but you can also see it spread out a whole lot more, whereas sample A is not spread out. The standard deviation is a lot less. Here the standard deviation is greater. So spreads are actually really important because we initially looked at these data sets and said, oh, they have the same mean, so they're on average they're the same, but they're spread out a heck of a lot more. B spread out a whole lot more than A. Notice these numbers are pretty close together. They're between 17 and 23. These numbers are not close together. They're between 5 and 35. So the spread is a lot higher here than it is here. So in statistics, when you're describing a data set, you want to talk about not only the center, but the spread as well. If you just focus on the mean, you might get in trouble. If you talk about center and spread, you pretty much described the most interesting things about the data set. It's going to help people out, help people understand what you're talking about, help you understand what you're talking about if you've never seen a data set before. Okay, this is kind of a fun little application problem to kind of get the idea of understand why spread is such a big deal. We have two 5th grade classes that have a nearly identical mean scores on an aptitude test. So let's just say the aptitude test is denoting their skill level in certain subject areas. But we have one class has a standard deviation that's 3 times that of the other. All other factors being equal, which class is going to be easier to teach and why? Okay, so they have the same mean score, which could be really nice, but one class has a standard deviation 3 times that of the other. That means that one class looks like this, whereas the other class might look like this. This is that same drawing I keep drawing. Even though these means might be the same, this class has students way down here and way up here and a few in the middle here and some over here and some, whereas this class has most of its students right here, a few kind of over here and a few over here, but nothing way down here and nothing way up here. You see why spread makes such a big deal? Is it easier to teach a class where everybody's pretty much at the same level, or a class where you have people all across the board? You have people way up here, really, really adept at things, and people really behind on things, and people kind of in the middle, and people kind of leaning behind. Is this easier to teach, or is it easier to teach people who are pretty much all on the same page? The answer is it's going to be easier to teach this group with less spread, because if everybody's at the same level, then you can teach them all the same way, and they'll kind of catch on about the same time. Whereas if you try to teach everybody on different levels the same way, they're not all going to catch on. It's going to be really tough. So this is more spread. So all this example was to demonstrate why spread is important when talking about a data set. It may seem silly that if they have the same mean, the data sets are that different or should be treated differently. But spread really can change the game in a lot of situations.